Now by equation of state, what we know here, P equal to rho RT. Upstream and downstream side, if we start taking the static pressure ratio, P2 by P1 is equal to rho 2 by rho 1, because gas constant will be cancelled out, and hence multiplied by T2 by T1. This expression will lead to. Now furthermore, from the continuity equation, because m dot is equal to rho AV, and hence since this across the flow process, a small, if you choose a small control volume such that from upstream and downstream, means here we are considering the flow which are very adjacent to this waves upstream and downstream. Essentially we are trying to make sure the area from upstream to downstream is constant. In such situation, rho 1 V1 is equal to rho 2 V2. Again using the equation of state, we can evolve P2 by P1 is in terms of velocity V1 by velocity V2 into T2 by T1. You can here say here by rho 1 V1 is equal to rho 2 V2. If you replace this fellow as RT1 into small v1 is equal to P2 divided by RT2 small v2, v1 and v2 upstream and downstream velocities, and hence you can lead to this expression. Now since velocity can be written as further as Mach number times square root of gamma RT, and hence P2 by P1 both upstream and downstream side can be written as this. And using this further, we can strike out the gamma into R, a constant term. We will lead to the final expression as P2 by P1 into is equal to M1 by M2 multiplied by square root of T2 by T1, and hence again using the T2 by T1 expression which we have already developed here from A, if you substitute this in this expression, then we will lead to P2 by P1 is equal to M1 by M2 square root of 1 plus gamma minus 1 by 2 M1 square upon 1 plus gamma minus 1 by 2 M2 square, and you say essentially this is the equation B, which is again the pressure ratio, static pressure ratio across the normal shock wave.